to next speaker, Professor Fred Adler in the Department of Mathematics from University of Utah. So he has PhD from Cornell University and had a very short postdoc at the UC Davis. And his research interest includes many aspects of mathematical biology, ecology, epidemiology, immunology, oncology, and virus dynamics. So today, he will be talking about how can we establish the conditions for adaptive therapy. So please take away.
Thank you. Am I audible and visible?
Yes.
Perfect. Okay, well, thanks for letting me be part of this. This has been a great meeting so far. I've learned a huge amount, and I'm hoping that this talk isn't too long so that we have time for questions and comments. This work is still in progress, and there's certainly a lot of room for improvement. And I look forward to your comments. So this is work done jointly. This started off with our U54 project run by Andrew Bild at City of Hope. And most of the work here has been done by Cassie Bueller, who was an undergraduate in my group and is now a graduate student in Drexel in some bizarre business program. So the outline is simple for this talk. We'll look at a variety of modeling frameworks, compare some results, and then end up with some general thoughts about where this might take us. Okay, so the general model framework is maybe slightly more general than what we've seen from Rob, whose analysis was really elegant of the S and R interaction. So all these models will have sensitive cells and resistant cells. The little flat-headed arrows indicate that that we're assuming, though we don't have to assume, that these things are repressing each other. There's treatment, capital T, or therapy that we have suppressing the sensitive cells, but also could and often does suppress the resistant cells to a lesser extent. And then there's something else in the world, this mediating factor. And this is what sort of our focus is on, is thinking about what are the consequences of different mediating factors in this system. And so there's many possible goals, which were discussed nicely by Rob just a second ago. We can minimize cancer burden, delay resistance, minimize side effects. Of course, ultimately, we want to extend survival and maximize quality of life for patients. We're going to only focus on one of these, delaying resistance, but of course, the other things can be derived from these models. So what are the models? So this is the original model that we've heard discussion of with Zhang, his first author, back in 2017. So this has a Lotka-Volterra structure. We have sensitive cells and resistant cells. This is to androgen therapies, and they're repressing each other. And then we have producing cells, so androgen producing cells. And they compete with each other, but these androgen producing cells also benefit the sensitive cells, which require androgen. And therapy operates really on this arrow by repressing this effect. It does so in a way that's somewhat hard to understand from a modeling perspective, but it produces a very effective model of therapy, of a very effective therapy. So what are the key assumptions? In this model, it has implicit androgen dynamics. That is, it's built into the way that this is repressed via the carrying capacity. It has that the sensitive cells are dependent on these producing cells. That is, that there's no other external sources of androgen. And the effects of the drug are extremely rapid and extremely strong in the way this is parameterized. Okay, one can then back off from that model and just go back to a vanilla Lotka-Volterra style model, which is, a very special case of what Rob just talked about. And here we have S and R cells suppressing each other in treatment. And it's all about competition. And you have to make various assumptions about how therapy works. And here we assume that treatment increases the death rate of cells. It could decrease their growth rate, of course. Then there's plasticity, which also has been alluded to, and I think we'll hear more about tomorrow, is that therapy can not only suppress cells' growth, but can alter their behavior. And we may have, in the worst case, the sensitive cells are smart, and the therapy alters their behavior so they become resistant, and maybe the resistant cells are smart too, and if therapy is taken away, they become sensitive again. And this, of course, is a kind of a worst case for therapy, because in terms of the game theory that we've been hearing about, yeah, the cells are stupid, but they're not as stupid as they could be. We can also then include an Allee effect. So Allee effect is a term from ecology, which says that to some extent that populations do better at higher populations. So in ecology, a typical mechanism is finding mates. So if there's a very tiny population of some sort of obscure wren in New Zealand, if there's very few of them, then they can't find mates and their population does poorly. Another example that's probably more common is protection from predators. So a larger group can spot predators and escape from predators more quickly. Allee effects can take two flavors. They can be a very strong Allee effect, which means, I don't know if I can make this thing go away. Nuts. Sorry about that. So in a strong Allee effect, the growth rate is negative at low population. So in this creates a population threshold. So Joel yesterday alluded to passenger pigeons, and there's some arguments out there that there was an Allee effect there, that when they got lonesome, when their populations got so small that these people shot them all, that they were too lonely and they couldn't breed. We say bred in huge colonies. A weak Allee effect means that populations don't shrink at small numbers, but they do more poorly at small numbers. So I've indicated this on this form of the generic diagram with this total population size benefiting with the positive arrows, both the S and the R populations. This can be asymmetric in a whole bunch of different ways. I've just made it the function of the total population size here. Then something that we've also mentioned in this, which has really bothered me for a long time, is that cancers do not grow in isolation. They grow in your body, and your body is made up of healthy cells. Healthy cells take on many, many roles in cancers. They compete with cancers. They can benefit cancers through delivering resources, many other things. So in the simple healthy cells model, it's just a competition-based model, and so that they are taking up space, as we've heard, and taking up space is good because the cancer cells can't elbow their way into it. In this version, healthy cells are not affected by treatment, which of course is our ideal, but as we know, side effects are often the consequence precisely of healthy cells being affected by treatment. The immune system is a form of healthy cell that interacts with cancers, sometimes in bad ways, that is promotes their growth, but in general in good ways, that is suppresses their growth. And so here's an immune cell model where both sensitive and resistant cells promote the immune system. They may do so differently, and the immune system here is suppressing those cells. It also may do so asymmetrically. As before, we assume, and though this is probably a touchier assumption, that the treatment does not affect the immune cells. As you know, many immune cells are rapidly cycling and can be affected by treatment. That, of course, could be included in these models. Then, as sort of an extension of the original model, one can make a more mechanistic androgen model, and so that the producing cells actually make androgen. And so what these drugs do is suppress these production pathways in various ways, and so they can either suppress this production of androgen or suppress other sources of androgen which do exist in the body. I ran out of space to draw arrows, but androgen is good for our sensitive cells, so there should be a positive arrow growing here. So from an ecological perspective, right, this is appealing in that it looks a little more mechanistic. This is a resource-based model. This competition can be thought of as competition for space, which is a perfectly reasonable assumption in the context of contact inhibition. And the other benefit of this, even though I forgot to draw the arrow, is that one can have more realistic drug effects, right? Is actually think about whether the drug suppresses production in different ways. And also one can think about mechanisms of resistance, which is very interesting to us. Okay, so those are the models. And there are others, but so our general philosophy was to take a look at these simple models, which are competition based, and think about sort of as an ecologist might, what are their consequences for the effectiveness of treatment. Okay, so what we did is ran in a fairly naive way a whole set of adaptive, intermittent, metronomic, and no therapy options. So metronomic is what I'm using for constant therapy. Maximum tolerable dose, you could say, is just a high version of constant therapy or a low version of constant therapy. Intermittent therapy, we ran a whole range of different cycle lengths, 600 on, 200 off, and so forth. These parameters are not necessarily completely realistic. And for adaptive therapy, we did the same thing. So instead of just running a turn on therapy, say when tumor burden reaches 90% of some threshold, and turn it off when it's at 50%, we tried various level values of 90% and 50%. So that's what generates these curves. So we have a whole bunch of adaptive therapies and a whole bunch of intermittent therapies. Here we're comparing two outcomes, and we're only looking at one target of therapy, which is maximizing time to escape. That is, for the resistant cells to grow to some low threshold. And then on the vertical axis, we're plotting cell count. So how many cells are there? As we've seen, as Rob showed in a very nice general way, if models work on competition, then the only thing that stops the resistant cells is sensitive cells. And so we're going to have some kind of trade-off between these, right? So the good place to be is down here where I stuck the legend, right? We want really long time to escape, ideally infinity, and low cell count. So in models of the sort of Lotka-Volterra family, we see this trade-off, right? So if you slam them with treatment, this metronomic star, there aren't very many cells, but resistant cells pop right up. That's the lesson that Bob Gatenby and many others have taught us so elegantly. But as you move up, you can slow it down, but at the price of having more cells. There's a real question here of is that bad? And, one could argue tolerable tumor burden is great, but the concern, of course, is that additional mutations and additional metastases will occur if you allow a tumor to remain too large. So what the optimum is here is, I think, a clinical question, not a mathematical question. Another point to make is that adaptive in this context and intermittent therapies follow the same curve. And which makes sense, right? We're just really seeing there's one factor in play here, competition. Same deal with the vanilla Lotka-Volterra model, not surprisingly. The curve's a little different, but we see the same exact principle. Longer time to escape comes at a price of more cells. With plasticity, I don't show the results because in this case, we're only looking at the time to escape, that is emergence of resistant cells, and that happens immediately. And plasticity is a real problem. It's a real thing. And I think how to manage that will require a very different type of thinking than these ecological models. The Allee effect is rather interesting, however. So remember, an Allee effect means that cells do badly when they're rare. And here, I've put an arrow on it, you can actually get to the happy place. And for reasons I don't quite understand, and we're still working on this, our adaptive therapies all end up hanging around a really bad place, and I think that's just the choice of the therapy parameters. But some of the intermittent strategy parameters end up in the good place. Why is that? Well, that's because if you can knock the tumor below that threshold that exists when you have an Allee effect, great, you just won the battle, right? The Allee effect does it for you. Of course, whether there is going to be such an Allee effect is an empirical question. The healthy cells model turned out to be rather interesting also. So if you plot the same graph, we see the trade-off here, but then there's a whole bunch of them that are really slow to escape. And we only ran it for time 3000, but some of these I think will go indefinitely. And so the ideal ones are the ones that have the fewest cells and the longest time to escape. And here's some of the dynamics for that case. So this is our best intermittent strategy. And so you can see happens as with no therapies, here's the sensitive cells come zooping up and the healthy cells get knocked down. So you end up with this sort of half tumor unit, which may or may not be realistic. With maximum therapy, here come the resistant cells in green popping up. And that's because they're not as effectively suppressed, right? But with this appropriate intermittent therapy, which is showing these cool wiggly lines, right? It can suppress the resistant cells and keep more healthy cells around. So that's an interesting result. The immune cells model, surprisingly, followed basically the same exact trade-off that we've seen elsewhere between time to escape and cell count. And finally, the same deal with the mechanistic androgen model. And I should confess that when I started this work, I was convinced that this would be really different, that I've criticized the original model for its sort of unrealistic handling of resources, and it proved that it really didn't matter. I should say that this separation between the adaptive and intermittent therapies is just a byproduct. And in this case, we looked at a smaller set of intermittent therapies, so they do also cover the full range of this curve. Okay, so people are probably wondering, what does this have to do with COVID? And so I'm going to tell you. So in ecology, we really study, in my view, one thing: population regulation. And population regulation requires density dependence, that is nonlinearity. In the absence of nonlinearity, things will either grow or decline exponentially, which is not sustainable. Of course, exponential decline would be a great thing for cancers. Where's the density dependence? That's what we ask. Evolution is driven by that density dependence. And so what do we see with SARS? So here's a picture of a person with SARS. So evolution is driven by that density dependence. And in SARS, at the moment, we have minimal density dependence. You know, despite the large number of cases, there isn't very much competition between different flavors of the SARS-CoV-2 virus. And we're seeing very little evolution, despite what you may have read in the press. D614G, in my opinion, is a blip compared to the kind of evolution one would expect to see from an RNA virus, which mutates even faster than cancer cells. And here's a picture of a person with lung cancer, which you notice is identical to that of a person infected with SARS-CoV-2. And the mechanisms of density dependence are critical. And as was mentioned in, forget if maybe it was Jill's talk, about metastases, or early fast-growing metastases may look much more like SARS-CoV-2 in its initial phase, and thus not be experiencing very much competition, and therefore the evolutionary pressures on it are much weaker and potentially quite different. So what have we learned? So for models of this class, which is a very simple class, adaptive therapy and intermittent therapy are basically the same. The optimal strategy does, in some cases, depend on the structure of the system. So why is adaptive therapy a better idea than this may look? I think one of the real strengths of this is it naturally adjusts to patient parameters. One of the things that's left out of these models is everybody's the same. And that's why those trade-off curves look so perfect. Of course, people aren't the same. Choosing the right intermittent strategy for one patient might be a terrible one for another. Adaptive therapies adjust to that patient's dynamics, and I think therefore can find better places on that curve that are much more robust to patient-patient differences. But I do think we need to understand the mechanisms of interaction to find the right target therapy levels and timings. And lastly, and this is what our group works on, is trying to integrate, and Rob just showed a beautiful example of this, integrating models with in vivo and in vitro data is going to be key to establishing what these mechanisms are and then being able to capitalize on those mechanisms. Okay, that's the end. Thank you.
Okay, thank you. Very nice introduction for different kinds of models. So we have a couple of questions for you. So first one is from Heiko Enderling. So thank you for a nice overview of different models and treatment implications. Based on the considered models with different treatment outcomes, how many data points do you think we will need from individual patients to know which model their disease follows?
A great question. I don't know. I would say, based on our experience, more than 3. But I would say that, I mean, I guess there's 3 dimensions to this. There's how many data points per patient. There's how many patients, and then more patients gives you more power because you can treat them as random effects. And then there's what you can do in the lab. And so my hope, and this is obviously not an answer to your question, is that by combining those 3 things, we actually can get insights into individual patients from very few data points by knowing what the mechanisms are. So for example, if we know the mechanism of resistance, if we can take cells from a patient, bring them in the lab, establish say the proportions of sensitive and resistant cells that way, then we should be able to get a sense of which mechanism is in play in a given patient. But that, at least in our group, is yet to be done. But that's a great question. Thank you.
Okay, thank you. So the second question is from Sandy Anderson. So all of your models explicitly ignore space and assume a well-mixed dynamics. Do you not think space is relevant there?
Space is, of course, relevant. And yeah, and I've certainly been convinced by that even more in the last couple of days. My hope is that we can extend these models to have a cartoon version of space, that is to capture this distinction between the growing boundary and the non-growing center without having to go full bore PDE. And that remains to be done. I think it is actually possible to have a cartoon version of space that gets at least some elements of that.
Okay, thank you. So next question is from Elsa. Thank you for explaining how all of this relates to COVID. So, she's complimenting. So she's waiting for this. And the next question is from Joel Brown. So can
you can ignore that.
Yeah, can your results suggest when we can use ecological abstraction and reduce the model's dimensionality versus retaining all moving parts?
Yeah, that is a great question, and thank you for not slaying me. That's the ultimate question for me as a modeler. My feeling is we actually can be quite successful with models of this level of complexity or slightly greater. That is including certainly a simple version of spatial competition, as Sandy suggests, and maybe a few other things. We're going to use ecological abstraction no matter what, right? And so the question of finding the right level of abstraction remains. But I am actually pretty convinced, based on, say, the analysis that the Moffitt group has done with prostate data, that we're going to be able to get away with models of this level of complexity. And my hope is that by having a slightly broader framework, sort of as Rob laid out, we can choose intelligently our strategy and identify the complexity. But at least for me, that also remains to be completed.
Okay. So the next question is from Helen Moore. So you mentioned random effects. Have you used mixed effects modeling to estimate parameters and better understand the variability in their values?
Yeah, I mean, that's in progress. I mentioned in answer to Heiko's question that we have a really great data set from a clinical trial where we have 3 data points per patient, but 60 or 120 patients, depending on which data set we're looking at. And yeah, we are analyzing those as random effects, which I do think gives us a lot more power. And there, of course, we have clinical outcomes. So that's great. So we can link it with clinical outcomes. So yeah, that's work in progress. And we're hoping to combine those 3 pieces, models, clinical data, and laboratory data, to really understand what's going on in patients.
Okay, so she has a following up question. So to account for variability between patients, have you looked into robust solutions that can be good for a group of patients rather than the optimal solution, which can be good for one but bad for others? Good for one, but bad for others.
Yeah, that's a great question. No, we have not done that. I sort of hinted at that here at the end in terms of the value of adaptive therapy, but certainly that's a great idea, and we will try to follow up on that.
Okay. So the last question is from Audrey Frister, and each of these models focus on single interaction between resistant and so on. Would you expect any changes in the dynamics when you combine all of these into a single model?
That does sound like a fun thing to do, which I am going to have to try. I'm guessing that, for most of them, they sort of all did the same thing, which is they were models of competition. I don't think it'll matter much. The Allee effect kind of runs the show. That is, if you get below an Allee threshold, that's the end of the story. But yeah, at some point, I will throw the whole kitchen sink together and see what happens. I don't think it'll be that interesting, to tell you the truth. So it'll probably end up in the supplement. But thanks for the push. We'll do it.
Okay, thank you. Thank you for your great talk. So